Welcome to This Explainer. Today, we're going to demystify what can often feel like the most abstract part of algebra. We're going to visualize mathematical relationships not just as floating numbers on a page, but as a series of physical, interlocking links. We're mastering continued proportion, and specifically, what we'll be calling the chain method. To start off, we really have to tackle a fundamental problem. How do you take distinct, separate variables, like an A, a B, and a C, and find a logical, mathematical way to connect them seamlessly? In our source material, this isn't just some theoretical exercise. It's a foundational skill for solving complex equations and understanding relative values. We need a structure that binds them all together. Here's our roadmap for today. We'll cover the proportion chain link, deriving the mean proportional, AI and the math algorithm, extending the math chain, the master key K, and finally, unlocking complex proofs. Let's get right into it. Section 1, the proportion chain link. So here is the formal definition from our text. Continued proportion happens when quantities A, B, and C are proportional, forming this overlapping sequence, A over B equals B over C. And this brilliantly illustrates how the letter B acts as the interlocking ring. In math, B here is called the mean proportional. It physically and conceptually holds the first proportional, A, and the third proportional, C, together. Without B bridging the gap in both of those fractions, the whole chain just snaps. Section 2, deriving the mean proportional. We can follow a very logical progression here to unroll this chain. Step 1, we set up our equation. A over B equals B over C. In step 2, we execute the physical action of cross-multiplication. Grab the extremes, that's A times C, and grab the means, that's B times B. This brings us right to step 3, revealing the derived property, B squared equals AC. By doing this, we can clearly see exactly why B squares itself. It's literally just the direct result of cross-multiplying that interlocking joint. So the crucial point is how this works in practice. Let's say you're looking for the third proportional for the numbers 6 and 18. You simply apply the rule. You set 6 over 18 equal to 18 over x. Cross-multiply and you get 6x equals 18 times 18. Solve for x and boom, you land on a final answer of 54. The math does the heavy lifting for you for sure, as long as you set up that chain correctly. Section 3, AI and the math algorithm. Now, you might be wondering why we're drilling down into fractions and cross-multiplication. Well, the source textbook actually explicitly asks if proportion concepts can be developed in artificial intelligence applications, complete with this really striking image of a robotic figure. It reminds us that this chain method, taking relative inputs, processing them through a consistent interlocking logic, and generating an output, is essentially the absolute blueprint for an algorithm. AI relies heavily on scaling up this exact kind of relative proportional logic to process massive sets of complex data. Section 4, extending the math chain. When we generalize continued proportion for 4 quantities, the chain just gets longer, but the logic remains totally identical. A over B equals B over C, which equals C over D. Here, B is still our mean proportional between A and C, but now C becomes the new interlocking mean between B and D. The links just cascade. You could literally extend this to infinity and that interlocking structure would never fail. Section 5, the master key K. All right, looking at the left side here, we have our extended chain. A over B equals B over C equals C over D. These are entirely relative, constantly shifting values. It's kind of like a house of cards. But on the right side, by setting that entire extended chain equal to a single non-zero constant, which we're going to call K, everything changes. We unlock a master key that allows us to substitute every single relative letter with a concrete, calculable value anchored directly to K. And the substitution rules follow an incredibly elegant design. Just notice this beautiful pattern. As we step further up the chain from right to left, the exponent of K simply escalates. C is just D times K to the first power, B becomes D times K squared, and A becomes D times K cubed. It just counts up, 1, 2, 3. This makes substituting these values into complex equations incredibly intuitive, rather than a frustrating chore of rote memorization. You just find your anchor, in this case D, and count up the K exponents as you move left down the alphabet. Section 6, unlocking complex proofs. Let's put this to the ultimate test. This is a classic algebraic proof directly from our source material. It demands we prove that the complex, pretty intimidating fraction on the left side, a squared plus c squared over b squared plus d squared, is perfectly equal to the fraction on the right,
AC over BD, given that they're all in continued proportion. I mean, trying to solve this by moving the letters around directly, absolute nightmare fuel. But we have our master key, K.
By plugging in our escalating K values, remembering that A is dk cubed, B is dk squared, and C is dk, we completely transform the problem. By visually stacking the substitutions, we factor out the common terms. On the left-hand side, those messy k to the fourth plus 1 expressions, they cancel each other right out, and it all boils down beautifully to just k squared. Then we do the exact same simple substitution on the right-hand side. The d squared cancels out, we subtract the exponents on the k's, and yep, it also simplifies perfectly down to k squared. By anchoring everything to our constant k, we flawlessly prove that both the terrifying left side and the simpler right side reduce down to the exact same value. Proof complete. So, what does this all mean? Well, this explainer shows us that what looks like chaotic, unmanageable algebra is actually just a series of deeply organized, predictable links. As you take these MapRadical tools into your own studies or work, it's really worth asking yourself a fundamental question. What foundational chains are holding your own complex projects together? Remember that whether you're an AI mapping out massive data sets or a student just trying to solve for K, mastering the basic links is absolutely the key to conquering the entire chain. Find your constant, establish your structure, and the complex proofs will practically solve themselves.